everyone, welcome back to my YouTube channel. As you can see here, this was a Taylor series I found in another one of my videos. If you want to know how to find a Taylor series of this function, you can find the explanation in another one of my YouTube videos. So we have found this Taylor series right from the other video. So now in this video, we are going to learn how to find the radius of convergence as well as the interval of convergence for this Taylor series. So we're gonna do that today. Okay, so this is the series, okay, that we need to find the interval of convergence and the radius of convergence for. So in order to do that, we must use the ratio test. The ratio test looks something like this, okay? I did explain this in another one of my videos, so if you want to see the ratio test, some other examples from that, you can feel free to check that out in my channel. So anyways, we have to evaluate the limit for this, right, in the ratio test. So here, our an is this whole thing. Right here, this that I'm boxing in is our an, okay? So this is our an. So an plus 1, we have to take the n's and add 1 to it. So we're going to do that. And doing that, we are going to get -1, and this is n plus 1, right? This n becomes n plus 1. It's 5, right? This is n plus 1. This n is going to be n plus 1, so we have to add another 1 as well. And then here it's x minus 5, and then n plus 1. And we have to divide this by basically the original one. So we just have to copy this. Okay, so now we have this, and now let's flip the fraction, okay? Second fraction. And in the meantime, while we do that, let's save some time. So let's change this to -1 to the exponent of n times -1 to the exponent of 1, because we're adding these exponents, okay? According to exponent laws, we add these two together and we will get this. So let's just take apart this, okay, and make it like this. Okay, so we can cancel stuff out with with what we're dividing, right? So this is n x minus 5 to the exponent of 1, right? Same concept, add these two together, you will get this. So I'm just taking that apart so we can cancel stuff out with this second fraction later on. So here, 5n plus 2. This 1 plus 1 is 2. We're going to take this apart in the next step. We can flip this fraction as mentioned before, so flip. Denominator goes on the top, numerator goes at the bottom. In the meantime, let's cancel some stuff out. Let's cancel this, and this one, and this one. Okay, perfect. Now let's carry on to this next step. We have -1 here to the exponent of 1, so it's just going to be -1, and then times x minus 5, and then this is 5n plus 2, right? So let's change this to 5 to the exponent of n times 5 to the exponent of 2. Add these two exponents together, we will get this, okay? Times 5 to the exponent of n, and then 5 to the exponent of 1, right? And that is because we have exponent law, so we can add these two exponents together, we will get n plus 1 right here. Everything's cancelled here, so just write 1 here. And then, let's see, we can cancel some stuff out. Let's cancel this, cancel this. We can cancel this with this, so this will have no more exponents, just exponent of 1, right? And then, right, because we subtracted 1 from this exponent, subtract 1 from this exponent, so it's just going to be 5 to the exponent of 1. So on to the next step, we have limit n to infinity. Here it's -1. Let's just rewrite everything first. Might make things easier to look at. It's a 5 to the exponent of 1, so it's just 5. Absolute value sign. And then now let's look at it, and we know this is negative and this is 5, right? So this part, this negative 1 over 5, well, it's in the absolute value sign, so let's take it out with the absolute value sign and get rid of this negative, because the absolute value of negative 5, 1 over 5, is going to be 1 over 5. So it's just going to be 1 over 5 right here. Take it out of the absolute value, right? As we get rid of this negative, it was a negative and an absolute value of this, like absolute value of this, it's going to give us 1 over 5. So that's why it's just positive 1 over 5 right now. So x minus 5 is not guaranteed to be positive, so let's put absolute value signs around it, okay, because it originally had absolute value signs. Now let's evaluate the limit. Well, if we evaluate the limit, there's no ends, so that would just basically tell us that we can get rid of this limit part, right? There's no ends, so it's just 1 over 5 times the absolute value of x minus 5, and there we have it. So this is our ratio test. Now, how can we ensure that it's convergent? Well, we know from the ratio test that if the limit, right, when we evaluate this, okay, the limit of this, if it's less than 1, then that means it will be convergent. So we want to ensure that it's convergent, okay, because we are, after all, finding the radius of convergence for this and the interval of convergence. So to do that, we're going to take this and we have to say that, oh, this has to be less than 1. This is our limit, right? This whole thing is our limit, so it has to be less than 1 in order for the series right here to be convergent. So let's write that, and let's kind of like solve for it. So let's take this 5, move it to the other side. Actually not really solve for it, but let's put it this way. We know that to find the radius of convergence, we know that it's like absolute value of x minus a, some number a, right? Being less than r in order for the series to converge, right? In order for a series to converge, this must be the case. So the r in this case, right, if we have it in this format, and we do right now, x minus a is less than r, and our r in this case, if we corresponded, r is going to be 5, right? So our radius of convergence is therefore 5. Now, we have to find the interval of convergence as well. So to find the interval of convergence, we basically continue this part, right? So x minus 5, 5. To continue this part, to remove the absolute value sign, we will get the following, right? This is going to be between negative 5 and 5. And to visualize this on the number line as to why this is the case, well, we have 0 here, okay? So let's say we have 5 here, let's say we have negative 5 here. So this has to be between negative 5 and 5. So let's say this was negative 4, okay? Let's say we have negative 4. So let's say x minus 5 was negative 4. So let's say it's negative 4. So that absolute value of negative 4, right, from here, is going to be less than 5. And that is true. And that's because 4 is less than 5. So absolute value of 4 is less than 5. So you can basically say that, well, you see negative 4 is greater than negative 5, right? So this is like our negative 4 is greater than negative 5. So it works for negative numbers too. And we know similarly, if say it was 4, like if x minus 5, the absolute value of that is 4, right? Absolute value of 4 is going to be less than 5, and that is true. Okay, that is true because 4 is less than 5. Indeed, it is true. And 4 is less than 5. So with negative numbers, to visualize it this way, is we can say, oh, well, let's say absolute value of x minus 5 is negative 4. So like let's say it was negative 4, right? This whole thing here was negative 4. The absolute value of this is going to be less than 5. And that is true because the absolute value of negative 4 is 4, right? And 4 is indeed less than 5. So that's just an example of why we would change it to this. So changing it to this, now what we can do is we can solve for x, like put x by itself. So we're going to add 5, right? This is subtract 5, so the opposite is add 5. So negative 5 plus 5 on this side. Here 5 plus 5 on this side. Negative 5 plus 5 is going to give us 0. 5 plus 5 is going to give us 10. So this is x has to be between 0 and 10. Now we have to check to see if let's say if it could be equal to 0 or equal to 10, right? X is equal to 0 or 10. So to check that, we basically look back at our original series. We have to plug in x equals 0 and 10 into here as shown below, right here, right, these endpoints, to check as to whether this series converges or diverges when x equals 0 and when x equals 10. So here we have our original series, okay? And we're going to plug in x equals 0 and x equals 10. We're going to check it at the endpoints. So to do that, we basically plug in x equals 0. So plugging that in, we are going to copy this first. So x is equal to 0, so 0 minus 5 to 12n. And then we are going to get the series as negative 5 to the exponent of n. And then here we can see that we have these exponents added together, so split that up. N plus 1 is going to give us n plus 1 here, right? I mean, we're multiplying it, right? Exponent laws right here with the same base. So we can split that up. And here, exponent laws as well. So this is 2 exponent of n, right? The negative here is negative 1. This is 5 to exponent of n as well. So we distribute to a negative and distribute to a 5 like that. So now we can cancel stuff out. Cancel this, cancel this. And then this negative 1 to the exponent of n times negative 1 to the exponent of n. We basically do n plus n, right? Exponent laws over 5 to exponent of 1, which is just 5 here. And then here we know it's going to be 2n. And this tells us that this 2n is always going to be even. Right? It's always going to be an even number. And since we have an even number, then this is always going to be equal to positive 1. Because we're going to always have a positive exponent, right? And if it's like, even if it's an odd number, like if we do 2 times 3, like 2n as being 2 times 3, n being 3, it's going to give us 6, right? And if it's 6, well, negative 1 to the exponent of 6, just going to give us 1. That's for example. So that's why, well, here, since it's an even number, that's why it's just going to be positive 1 here. So we can rewrite this as positive 1. 1 over 5. So from here, we can see that this is 1 over 5, right? And then we can use the test for divergence to prove that this is, in fact, divergent. So with the test for divergence, we look at the limit. N goes to infinity for an. And this here is our an, right? 1 over 5 is our an. So we can just take the limit of that. N goes to infinity. And here it's a constant, so there's really no n in here. So this is just going to go to 1 over 5. And the test for divergence basically says that if this limit, right, is not equal to 0, like limit as n goes to infinity, an, if it's not equal to 0, then that basically means that the series will be divergent. And here it's not equal to 0. 1 over 5 is not equal to 0, and so therefore, by the test for divergence, so by the test for divergence, this series right here, right, when we plug in x equal to 0, this series is going to be divergence since 1 over 5 is not equal to 0. The series diverges when x equals 0. Now to check the next endpoint, which is if x equals 10. So if x equals 10, well, we're going to plug in x equals 10 into that series. So our original series, we're just going to plug it in to this series right here when x equals 10. So we're going to plug in 10 right here. So from that we will get the following. So n equals 0 to infinity, and then -1 to the exponent of n all over 5 to the exponent of n plus 1 times 10 minus 5 all to the exponent of n. This here was x as shown here. This here was x, so we plugged in 10 right here. So now from here we're just going to simplify this. So n equals 0, -1 to the exponent of n all over 5 to the exponent of n times 5 to the exponent of 1. Because this is exponent laws, you can add n plus 1 and you will get this. 10 minus 5 is going to be 5, and then this is to the exponent of n. And then here we can see you can cancel these, and here we will be left with the following: -1 to the exponent of n all over 5. We can rewrite this as 1 over 5 times -1 to the exponent of n. We can take this 1 over 5 out, right? So taking that out, we will get 1 over 5 times the following. And here we can change this -1 to the exponent of n to a geometric series. So looking just solely at this part, right? So looking at this series by itself, just this series, we can see that when n equals 0, right, it starts at n equals 0, so -1 to the exponent of 0, this gives us 1. When n equals 1, right, the next one be -1, and then -1 to the exponent of 2, it's going to be 1, so it alternates. So -1 to the exponent of 3, -1 right here, so it alternates 1, -1, +1, -1, +1, so on and so forth. So here we can see this is a geometric series. So the starting term, a is equal to 1, and then you will multiply by -1 to get -1 here, multiply by -1, right? -1 times -1 is going to give us 1, and multiply by -1, -1 times 1 is going to give us -1, and so on and so forth. So our r common ratio is going to be -1. So geometric series has the form a times r to the exponent of n minus 1. So in this case our a is 1. So our a is 1. So it's going to look something like this. This is our a. Our r is -1, so -1 is here. Plug that in, right, for r. Then all to the exponent of n minus 1. So in this case, we know this is a geometric series. So knowing this, we know that a geometric series, it converges when the absolute value of r is less than 1. So it converges when this is the case. And here, it's not less than 1. But also we know that the geometric series, it diverges when the absolute value of r is greater than or equal to 1. In this case, our r is equal to -1, so our absolute value of r is going to be equal to the absolute value of -1 from here. and the absolute value of -1 is equal to 1. R, absolute value of R is equal to 1. So that means that, hey, it will diverge. That means this will be the case for this series. So this series will diverge. And we know that this series is the same series as this one right here. This series and this series is the exact same. They are rewritten, just rewritten with n equals 1, starting at n equals 1, because that's how geometric series works. Here it's just n equals 0. Exact same series, right? Because we wrote out the terms for this one right here, and from here we took this part and we made this into a geometric series type of format. And so we know our absolute value of R is equal to 1, and since that is the case, that would mean that this series diverges, and hence when x equals 10, right, we plug in 10 here. This series, right, when we plug in 10, which was simplified to this, right, this series is divergent, and multiplied by a constant, well, it doesn't change its like convergence or divergence, so it just means that this whole thing right here is divergent. So therefore, when x equals 10, this series diverges, and since that is also the case when x equals to 0 here, right, we found that the series diverges, okay? So series diverges when x equals 10 and when x equals 0. So the interval of convergence for this series of convergence will not include 0 and 10, so we use round brackets here, 0, 10, to illustrate the interval of convergence not including 0 and 10 for the values of x. Okay, this is the end of my video. Thank you for watching. Feel free to like and subscribe if you haven't done so already. And furthermore, I always love to know your thoughts on my videos, so feel free to leave a comment down below. I hope to see you next time for another math video. Bye!